Let's spend some time discussing the multiplicity, and that's defined as the number of peaks in each signal. And this comes from magnetic effects of neighboring protons. So by observing the multiplicity, which we can see several examples down here, of our signal, that gives us a large amount of information as to the environment that this proton is in, as far as how many neighbors it has, how many hydrogens does it have right next to it. Let's look at a few examples. I'm going to put some X groups on here, which are defined as not having any hydrogens attached to them. We don't care what they are, just that they don't have any hydrogens. And we want to look at the signal of HA, and that's going to be 2. And we're going to follow the n+1 rule. N is the number of neighboring hydrogens. There is only one. Only HB is neighboring to HA, so the n+1 is 2, so we'd expect HA to have 2 signals in its, or 2 peaks, I guess, in its signal. How does that happen? Well, HB can be aligned with or against the magnetic field of the instrument. So what this means is it has a spin state that could either be up, we call that an alpha spin state, aligned with, or it has a spin state that can be against the magnetic field. We call that a beta, and this produces 2 signals very close in energy for HA. And so that's what we get when we have this doublet. These are actually 2 different signals from HA because it's affected either more strongly or less strongly by the magnetic field, because the adjacent hydrogen either adds to the magnetic field of the NMR spectrometer or it subtracts from the magnetic field of the NMR spectrometer. And so we get 2 signals separated by a very small amount, and that gives us this doublet. If we looked at this setup, what if we have 2 HBs next to our HA? The signal of HA is n+1. N is 2 in this case, so we get 3 peaks. And we get a signal that looks like this triplet here. And you can see how in the doublet, each peak was identical in height. In this case, the triplet has a peak that's half as tall as the middle peak on either side of the middle peak. So we call that a 1:2:1 ratio for that triplet. How do we get that? Well, again, we have 2 HBs. They can both be aligned with the magnetic field, or one can be aligned with, one can be aligned against the magnetic field. And since we have 2, we can reverse this situation and have the first one aligned against, the second one aligned with. That would produce equal amounts of the same amount of energy, and so the signal that's produced by both of these would actually add together, and we could have them both aligned against the magnetic field. And so when we add these up, we get a 1:2:1 ratio, because this middle situation occurs twice as often as the 2 outside situations. And so that's what gives us the 1:2:1 ratio for the triplet. So let's look at what happens if we have 3 neighboring hydrogens, 3 HBs. So the signal of HA equals 3 plus 1, n+1 is 3 plus 1 equals 4 peaks, because there are 3 neighboring HBs to this neighboring HA. That's what we're focusing on. Each of the HBs will align with or against the magnetic field of the instrument, affecting the chemical shift of HA. And so we need to draw a number of different possibilities with the 3 different HBs. So the first possibility, of course, is that they are all aligned together. Then we can have one of them aligned against the instrument, and we can have, there's three different possibilities of the same setup. We can have a different of the three HBs aligned with the instrument, or aligned against the instrument. And so you see that each of these are considered to have the same energy, and so they will actually add to each other, and their effect will appear at the same chemical shift when we look at the signal for H8. Another possibility is to have two of the HB signals be aligned against the instrument. And we get three different possibilities for that as well. And the last possibility is all three HBs are aligned against the magnetic field of the instrument. And so you can see here I have four different energy values, one with them all aligned together with the instrument, one of them the HBs are all aligned against the instrument, and then we have three different possibilities where one of the HBs is aligned against, and three different possibilities where two of the HBs are aligned against. And so these signals will add together to give us a 4-peak signal that has a ratio of heights of 1 to 3 to 3 to 1. And we see that same ratio here when we add these different outcomes together. And that's where we get the 1 to 3 to 3 to 1 quartet. And that's going to be very indicative of a quartet. There might be times where you see a signal that looks like this. 4 lines together, all equivalent height. That is not a quartet because it does not have the 1 to 3 to 3 to 1 ratio. And this would be called maybe a doublet of doublets, and that's something we'll talk about more in class as we get into a little more complex splitting patterns. But this is how this outcome, or these spin states and how they add together, are how we get to the 1 to 3 to 3 to 1 ratio for a standard quartet. Let's look at some more examples of splitting patterns. I'm going to add some hydrogens here and color code them. In butane, hopefully you'll recognize that we have two different types of hydrogens. We have the methyls on the end and the CH2s in the middle. And when it comes to coupling, let's look at the red hydrogens first. The CH2s will not couple with their equivalent neighbors. These CH2s are equivalent by symmetry, and so they will not couple. And so when we look at this CH2, we expect it to have 3 nearest neighbors, and thus it should be a quartet. So 3 nearest neighbors, 3 plus 1 equals 4. Let's look at the methyls then. The methyl groups are equivalent, again, by symmetry, and of course they have undisputably only 2 nearest neighbors, the CH2s. So for the methyl groups, we would expect n plus 1 is 2 plus 1. We would expect a triplet for that signal. And in this case, we would expect integrations for the methyl groups to be 6, because these are equivalent methyl groups. So we should have 6 hydrogens in this region that show a triplet altogether, and we should have 4 hydrogens in the region that shows the quartet altogether. Again, because they are equivalent, they would have the same chemical shift. Let's look at the CH2 next to the chlorine on this propyl chloride molecule. Of course, the chlorine has no hydrogens, but there are 2 hydrogens right here that I haven't drawn yet, so this 2 hydrogen signal should be a triplet, because it is adjacent to 2 other hydrogens. Let's draw those hydrogens. We'll use red in this case. And I'm going to draw the last hydrogens too. So the red hydrogens are an interesting case. I hope you would agree that this molecule does not have any symmetry. So I have 3 different color hydrogens. They are corresponding with 3 different types of hydrogens, 3 different chemical environments. The red hydrogens are next to a CH2 on the right and a CH3 on the left. So the red hydrogens should be 5 plus 1 equals 6, a sextet. We should have 6 lines in the signal for this CH2 because it is adjacent to 5 inequivalent hydrogens. It doesn't matter really that these hydrogens are not equivalent to each other. They will still add together to give us 6 lines in the signal for the red CH2. Sometimes this 6-line signal gets a little complicated, but right now let's just understand that there are 5 nearest neighbors, so we should get a 6-line signal for the red hydrogens. And then of course for the methyl, it is next to simply only the red hydrogens. That would be another triplet in this case. So the green hydrogens are a triplet. It is very common to see a 3-hydrogen triplet in the methyl region of molecules. Okay, let's look at this molecule down here. We've got, I think, 3 different types of hydrogens. There are 9 hydrogens on this T-butyl group, and we see 0 neighboring hydrogens on this central carbon. So each of these methyl groups is the same by symmetry. Each of these methyl groups has 0 nearest neighbors, so we would expect a singlet as the signal for all 9 of those hydrogens. So we'd expect a very high single peak, 9 hydrogens. If we look at the other side of the molecule, we have an isopropyl group, which also has very unique splitting patterns associated with it. Let's look at the 2 methyl groups. By symmetry, those are the same, so that would be a 6-hydrogen signal, and they are adjacent to only 1 hydrogen in the middle of this isopropyl group. So these methyl groups here should be a 6-hydrogen signal, which is a doublet. If we have 1 neighbor, n plus 1 equals 2, we should expect a doublet for these 6 hydrogens here. And lastly, we'll put the last hydrogen in. How many nearest neighbors does this blue hydrogen have? It should have twice a methyl group. It has 2 methyl groups. It should have 6 nearest neighbors. N plus 1 is 7 in this case. So we'd expect a 1-hydrogen septet. And that means there are 7 lines in the signal, in the splitting pattern for this blue hydrogen, because it is adjacent to 2 equivalent methyl groups. So we'd expect to get 7 lines for that hydrogen.